Hi guys, good morning. Oh, today almost everyone is here. Wow, nice. So early. Very nice, very nice. Okay, so we'll start right away, people. So, yeah. So we were seeing what are the ways to disturb the equilibrium, right? After the reaction has reached equilibrium, how do you disturb it? And then if you disturb it, which side the reaction will move? That's what we have been seeing, isn't it? Right. So we started with Lee-Chartlius principle. Lee-Chartlius principle said whatever is causing the change in equilibrium, right? That effect should be minimized. The reaction is going to go in such a direction that the effect is minimized or opposed. So if there's increase in concentration of one of the say reactant, the reaction is going to move in the forward direction so that the concentration of reactant decreases. So those are things which we saw. So we saw, I think first one was addition or removal of reactants or products, right? Then we went on to see change in volume, right? So when I change in volume, what is the shortcut? Hmm? When I increase the volume, how which side the reaction has to move? Tell me. Did you understand the question? I asked if I increase the volume after I reach equilibrium, which side the reaction will go? How will you decide it? Hello. Hope everybody is there. I didn't mute myself, right? Okay. Guys, what happened? So sleepy. I was so
For
happy that
volume, right, sir?
yes, for volume. If I increase volume, what will happen?
Equilibrium constant will decrease, sir. And
Sorry?
QC will be less than KC.
No. I told you, right? See, okay. So I think you little forgot, right? So if you can remember, a change in volume when I have delta N is equal to 0. When I have this kind of reactions, there is no change, right? Because I proved it to you, right? So we took a reaction where I had delta N is equal to 0. You saw that all the volume terms are getting cancelled, isn't it? Right?
Yes, sir.
So now when I have delta N not equal to 0, right? At that time, I think I told you that the reaction is going to go to the side where I have more
Stoichiometric coefficient.
stoichiometric coefficients, right? Stoichiometric, I'll write it in the short form, stoichiometric coefficients, right? So now this is for change in volume, right? So same way, when I go for change in pressure, the same thing holds good. When I have delta N is equal to 0 kind of reactions, if you change the pressure, there is no change in the equilibrium, right? But when I have delta N not equal, this is for volume, right? So when I have delta N not equal to 0, when I have change in pressure, now here we know that pressure and volume are inversely related, right? So now I have to go to a side which has lesser stoichiometric coefficients, and this is for pressure, right? So if someone asks you, I have PCl5 giving PCl3 plus Cl2. Now, after the reaction has reached equilibrium, I am going to increase the pressure, right? Now, which side the reaction will go? Which side the reaction will move? Wait, I will ask someone in particular, maybe. That would be better. Hmm. Maybe Divya, can you tell me? Hope you're there, Divya.
Yes, sir.
Okay, were you absent for the last class?
Yes, sir. Absolutely.
Okay, fine, cool. Maybe then I'll ask Rahul.
Yes, sir.
If I increase pressure for this reaction, which side the reaction will move? Look at this. I said that this is the rule. Which side? Okay. What is the total stoichiometric coefficient on the product side, Rahul? What is the total stoichiometric coefficient on the product side? Are you putting it in the chat box? Maybe, I don't know. It's not there. What happened, Rahul? Are you there?
Yes, sir. Checking.
Okay, that's what. Let me help you answer these questions. So I'm asking in this side, like in the product side for this reaction, what is the total stoichiometric coefficients? In the product side, this is the product, this is the reactant, right? Okay, maybe I'll ask someone else. Okay, maybe Shruti.
Sir, it will move towards product.
It will move towards product. Okay,
I have
see.
a doubt.
Yeah.
Did you ask for change in pressure or it
Yeah,
was,
I asked for increase in pressure. When I increase pressure, what happens? That's what I
it
asked.
goes to lesser side. So then
Yeah, exactly. See, now if you look at it, I have one as to stoichiometric coefficient here. For this, it is one. So total stoichiometric coefficient is 2 on the product side, right? Now in the reactant side, there is only
That's
one.
the reactants I miss.
Yeah, correct, right? So this side, I have only one as a stoichiometric coefficient. So obviously, one is lesser. So obviously, the reaction is gonna move in the backward direction, right? So this is how you go for it, right? Fine. So anyways, so we saw three things, right? Addition or subtraction of is that reactant or products, or say change in volume, change in pressure. You have to remember this, guys. Like I don't. This is pretty easy, right? When I have a increase in pressure, lesser stoichiometric coefficient. When I have increase in volume, go to a side where I have more stoichiometric coefficients. That's it, right? Fine. So we'll move on. We'll move on to the next factors which can affect the equilibrium, right? So the fourth one is temperature, right? So now I told you that the equilibrium constant value is a constant value. It is not going to depend on the initial concentrations. It is not how much you initially give. That doesn't matter for the equilibrium constant. It is going to be constant how much, like irrespective of how much ever you're giving, in respect of the amount of the reactants or products initially present, right? It is just going to depend on how much is there in the equilibrium, right? Okay, so temperature, but if I increase or decrease the temperature, the equilibrium constant value change. I told you that Kc is dependent on the temperature, right? Fine. So now we'll see what will happen if I increase or decrease the temperature after I have reached equilibrium. Okay, now we cannot see it just like that. We have to classify reactions into two types for us to visualize this. One is my endothermic reactions, and the second one is my exothermic reactions. Okay, endothermic reaction and exothermic reaction. We know what is the difference between these two, right? Endothermic reaction gives me heat, absorbs heat, right? And exothermic reaction will release some amount of heat, right? So that's the basic difference between endo and exothermic reactions, right? So now if you increase or decrease temperature for exothermic or endothermic, it is going to have a different effect on both these reactions. Okay, right. Now, how will I visualize it, right? So now if I want to write an equation for an endothermic reaction, this is how I can write. Say reactants will absorb some amount of heat to form products, correct? Right. So what I can see here is that the heat which you're supplying is going to act as one of the reactants. Now, it's not exactly that way, but you can just visualize it that way, right? The amount of heat you're giving, right, is taken up along with the reactants, and that drives the reaction towards the products, right? Okay. So now what happens if I increase the temperature for this reaction, for example, right? Any endothermic reaction I have, and if I increase the temperature, what will happen to the amount of heat? The amount of heat also increases, right? If temperature increases, the amount of heat also increases, right? So now what you're seeing here, indirectly, what I can say is that you are increasing the amount of reactants. Is it not? Because heat is coming in the reactant side, you're increasing the temperature. So the amount of heat also increases. So indirectly, what I can say is one of the reactants are increasing. The amount of one of the reactants are increasing. Right. Now tell me, if I increase the amount of reactants, which side the reaction should go? If the amount of reactants are increased, which side the reaction should go? Use Lee Chart-List principle, or you can use any of the text I told you.
So is it forward?
Yes, right. So you're increasing the reactant concentration. So the reactant concentration has to be decreased now. Which side it will happen? Definitely in the forward direction. Now, see, this is the way you can look at it logically, right? Say if I use my, say, no, I mean, in the sense that some other way, if you want to see it, like you can visualize it like this. Say now it's an endothermic reaction, right? So an endothermic reaction, you are supplying heat, right? So now if you increase temperature, that means what? You are supplying more amount of heat, right? So already the reaction requires some heat and you're supplying more amount of heat. So definitely it is going to move more and more in the forward direction. It is as simple as that. Again, I repeat, it's an endothermic reaction. It requires some amount of heat and you are supplying more and more amount of heat. That means the forward reaction is more and more favorable. The endothermic reaction is more and more favorable because you're supplying more and more amount of heat, right? So you can blindly say that if I increase temperature for if I increase temperature for an endothermic reaction, right, it is always going to move in the forward direction. Right, it is always going to move in the forward direction. Right, now same way if I see for an exothermic chemical reaction, say now how can I write it is something like this. One second, guys. Right. Right, so I have reactants giving products plus some amount of heat, isn't it? Right, so reactants are going to give products, and obviously, so in case of an exothermic chemical reaction, the heat is getting released. Right, now I can just look at it in the same way. Say if I increase temperature, the amount of heat released is going to get increased. Right, now what you're seeing, you're seeing that the amount of products are increasing, is it not? Because heat is one of the products, right? So the amount of products are increasing. Now according to Charles principle, I have to decrease the amount of products in the sense that I have to go in the backward direction, right? Or say I simply exothermic chemical reaction is giving out heat and you are supplying heat. That means obviously it is not going to favor the forward reaction. That means it is going to favor the backward reaction. Okay, so either way you see it this way or you see in terms of an exothermic chemical reaction or whatever it is, if you increase temperature for an exothermic chemical reaction, it is going to move backward. It is going to move to the backward reaction. Okay, it makes sense, right? It obviously makes sense if you just apply logic. It's nothing big, right? So endothermic chemical reaction, temperature increases forward direction. Exothermic chemical reaction, temperature increases backward direction. Again, I don't have to by heart it. Or you can just remember the logic. It's pretty easy, right? Okay, so that is about temperature change. After I reach equilibrium, if I change temperature, this is what is going to happen, right? Again, you have to decide whether first you have to know whether the reaction is going to be endothermic or exothermic, and accordingly only you'll be able to predict. Okay, fine. So next one, the last one, no, actually last two, I would say, right? Fifth one, which is gonna affect your equilibrium is addition of inert gas, right? So, right, okay. So now you can see what is an inert gas. Inert gas is one which is least reactive. Say I can have helium, argon, neon, all these are the inert gases, like the noble gases, the last group 18 family, right? So those the first three or four elements can be regarded as inert gases, right? So what I'm doing is that after I have reached equilibrium, right, to the vessel in which all these reactants and products are present, obviously it is going to be a mixture of reactants and products, is it not? So after the reaction has reached equilibrium there, I am going to introduce, say, any of these gas inside the vessel, right? And I'll see what happens, right? So again, for us to visual, I'll be able to do this in two ways, right? Addition of inert gas can be added in two conditions, I would say, right? So what are the conditions is addition of inert gas at constant volume and addition of inert gas at constant pressure. Okay, so addition of inert gas at constant volume and addition of inert gas at constant pressure. That means what? Like, for example, if I just look into this addition of inert gas at constant volume, right? I have to add inert gas, right? But the volume of the vessel, or say, assume that it is going to be a balloon kind of vessel, right? So obviously, if it's a balloon and I say I have this reaction happening, say, assume that, say, this is the balloon, right? Say I have N2, H2, and NH3, all of them are in equilibrium, right? Say, you know what is the reaction? Formation of ammonia, or say dissociation of ammonia is the reaction, right? This is in equilibrium, right? So now this is the balloon. Now if I introduce some, say, helium to this balloon, right, what will happen, right? So obviously, to compensate this amount of helium also, the balloon will expand, right? But that is not the case with constant volume. Constant volume, the total volume of the vessel should not change. That means it is going to be a proper vessel. It's a sealed vessel, right? So already all the things are there, N2, H2, and NH3, everything is there. And to this is the, say, stainless steel vessel, right? And it is sealed. To this, if you give helium, okay, to this, if you give helium, what is going to happen, we'll see, right? And this is the condition whatever I drew here, right? In the case of the balloon thing, that is exactly going to be the example of a constant pressure, addition of inert gas at constant pressure. Basically, if I do the process at constant volume, the total pressure changes. Okay, fine. We'll see one by one, guys. I don't want to confuse you. Okay, so first we'll take constant volume, right? So constant volume, this is the condition. I have a vessel in which the volume cannot change after adding the equilibrium, sorry, after adding the helium gas, the inert gas. Okay, now tell me, if the volume is not changing, right? If the volume is not changing inside this vessel after adding the helium gas, what property will change? Tell me. Again, I repeat the question. This vessel volume cannot increase or decrease, right? Now I already have some amount of gases there. Okay, so now I add helium to this. Some amount of helium I add. So the volume cannot change, but which other parameter of this vessel, or say of this mixture, will change? What will change?
Pressure.
Exactly. What pressure? Okay, now, okay, fine. Pressure is changing. Now I'll ask one more question. Now the pressure will change, obviously. Now what do you say? The total pressure, right? Say any before um, adding this helium, I say I had a PT, right? So before adding helium, I had, say, PT1 as a total pressure, right? Now after adding helium, the total pressure would have been PT2, right? Okay. Now, so we obviously understand that the total pressure inside this vessel is changing. Obviously, it is going to increase after adding helium, right? Now, my question is, we are going to have some partial pressures of H2, N2, and NH3, isn't it? Right? There'll be some amount of partial pressures of N2 and H2 and NH3. Now, the question is, will those partial pressures change because of addition of this helium? We obviously understand the total pressure is changing, no doubt about it. Now the question is, will the partial pressures of all these three components change? Will it change? Okay, so let me take a vote, right? Okay, so you can put it in the chat box, or say you can put it in you can unmute yourself and speak. How many of you feel that the partial pressures will change? Quick, I want everybody to participate. I want everybody to answer. Change or not change? should be our answer. Quick, everybody. It's just a guess. You don't have to be right. It's just a vote we are taking. Come on, put it in the chat box. Yes, okay. Divya says it will change. Then okay, Pranav says the partial pressures will change. Okay. Rohan also says it change. Okay, then how many participants I have? I have okay. Okay, 4. Okay, everybody changes change. Okay, fine. Then I have 2 more participants to give some answers. Okay, Venisha says it will change. One more.
So it will not change?
Okay, at last one. I think it's Shruti.
Yes, sir.
Okay, Shruti says it is not going to change. Okay, so this time the minority has won, so it is not going to change people, right? So how do we understand it? Okay, fine. Now the total pressure PT1, which I wrote here, that is the partial pressure of the mixture, right? That's the partial pressure of the mixture before adding helium, right? So what is total pressure here? It will be partial pressure of N2 plus partial pressure of H2 plus partial pressure of NH3, right? That is what is the total pressure here before adding your helium, right? Now, when I add your helium, what will happen? These partial pressures are going to remain same only. So I'm still going to have partial pressure of N2, whatever I had, plus H2 plus NH3, that is going to be there. And why is it that the partial pressure of 2 is increasing? I mean, the total pressure is increasing. It's just because of the addition of partial pressure of helium, right? Helium is also going to have its own partial pressure, right? So that partial pressure is added to PT1, that is the total pressure before adding. And that's why you're seeing that the total pressure after adding is increasing, because you're adding the partial pressure of helium to the available total pressure. Right? So that means what? The total pressure is changing, but the partial pressure values of the components are not changing. But what is changing is the total pressure, right? Total pressure is changing because of the partial pressure of helium. The other things are not changing, right? So I can even write PT2 as PT1. Oh God. Right. Let me write. Okay. I can write here maybe PT2 is equal to PT1 plus the partial pressure of helium. So this is the best equation which can explain you. The total partial pressure is not changing. That means N2s, H2s and NH3 pressure is not changing. The total pressure is changing just because I'm adding helium to this. The partial pressure of helium is just getting added to that. Okay, fine. Everybody understood? Guys, everybody understood? I hope how the pressure is not changing. Okay,
Yes, sir.
fine. Cool. Right.
So could you explain once again?
Yeah, sure. So the thing is, before adding helium, we say the pressure was PT1. Where was it? We said that the pressure was PT1. So let me see what is this PT1. PT1 is going to be a sum of the individual partial pressures. Partial pressure of N2 plus partial pressure of H2 plus partial pressure of NH3. Okay, right. Now I'm adding helium to this, right? So the volume cannot change, right? You only said that the pressure is going to change. That means the total pressure inside the container is going to change, and that is going to become PT2, right? So what is happening here? Basically, I already have some pressure, that is PT1, that is the sum of the partial pressures of these components, plus now I'm adding helium to this, so the partial pressure of helium just gets added up to the already existing pressures, right? So you see that there is an increase in pressure from PT1 to PT2 just because of the partial pressure of helium and nothing else, right? The existing partial pressures of N2, H2 and NH3 are not changing. That means the total PT1 before is not changing, but the overall total pressure is changing just because you're adding partial pressure of helium to this mixture and nothing else. That's why you see that the overall pressure is changing, but the individual partial pressures of the previous components are still intact. Okay, understood?
PN2, PH2, and PNH3 will all have the same thing.
Same value,
before and
exactly.
after.
Before and after, exactly. Yes,
Yes,
yes.
understood.
Right? Okay, right. So now we saw what happened. We saw what happens in constant volume. Right. Okay. Wait, it's not completed. So you see that the partial pressures are not changing, right? So if you see that the partial pressures are not changing, guys, what can you comment about the equilibrium? Is there going to be any change in the equilibrium, or whether there's no change in equilibrium? So let me put it in this way. Will the Kp value change after adding equilibrium? Will the Kp value before and after adding helium, will it be different or same? Kp value, the equilibrium constant.
So it should be different, right? So if you use that formula.
Okay, use that formula. What is the formula? If you write the formula, what is Kp?
P of product,
One
then
second.
raised to the power of coefficient
One second.
by.
One second. So Kp would have been a partial pressure of NH3 squared, right? You will just look at the reaction, you will understand why is it squared, divided by, oh god, this place is very bad. Okay, I'll write again, maybe here. Wait guys, I'll add a new page, or wait. Right, so if I write Kp as not concentration, it's partial pressure. So partial pressure of NH3 squared divided by partial pressure of N2 into partial pressure of H2 cube. This is what I'll have for the reaction, N2 plus
So
3
for
H2 giving
PT1,
ammonia.
this will be the reaction.
Okay, right. So now that this is okay, PT1, PT2. Okay, now the thing is this, that just now we told that this value, that is the partial pressure of NH3, partial pressure of N2, and the partial pressure of H2 are not changing even after adding the helium. What is changing is total pressure, right? But this total pressure has any role to play in Kp? No. Like the only thing which has some role to play in Kp is the partial pressures of all these three components, right? And these three components partial pressure are not changing even after adding your helium, right? That means what? Kp value before and after is gonna remain same. Yes.
Doubts.
Yeah.
Then we won't add helium to the denominator or something.
No, like why is it
Shouldn't we are adding it to the reaction also.
Yes,
So it
yes.
should be involved.
We are adding it to the
Kp.
vessel. Wait. We are adding it to the vessel, right? The reason we say it's an inert gas is because it is not going to take part in the reaction. So is it like I'm going to have N2 plus H2 giving NH3 plus helium? Is this the reaction? Right? Absolutely not. Right? This is not the reaction. This is not going to come in the reaction mixture. It is just going to be there in the vessel. That doesn't mean that it is going to take part in the reaction. And again, it will not take part of the reaction because it's an inert gas. We write Kp equation only for the reaction, not just anything and everything is there in the vessel. It's not like that. Right? Say, if I have, say, instead of helium, if I had put, say, some calcium into this, will you include calcium also? No, right? You are going to look at this particular reaction and you are going to take the species only in the reaction, not everything and anything which is there in the vessel, right? So even though you're adding, total pressure is changing, but the partial pressure values of all these three components are not changing. That means the Kp value is not going to change. that means there is no change in equilibrium. That is what you need to understand, right? This helium is just there in the mixture. The only role helium plays is to increase the total pressure. That's the only thing it does, right? Other than that, it has no role to play. It is not going to take part in the reaction. It is not going to do anything else, right? It is just going to increase the total pressure. And even though you increase total pressure, the partial pressure of these three components remains same, and so that the Kp value is not changing, and obviously there is no change in equilibrium. Even if so what I'm trying to tell you is at constant volume conditions, right? At constant volume conditions, if you add an inert gas, that has no effect, right? That has no effect. Right? So that's what you need to remember. Okay. So guys, any doubts from this? Any questions?
No, sir. Understood.
Right? Right. Okay. So it's pretty simple, guys. Right? What you need to understand is when I have constant volume, the volume cannot change. Only the pressure can change, in the sense that the total pressure can change. So the total pressure will change because you're adding the inner partial pressure of helium, right? So that other than that, it has no role to play. So the total pressure is changing, but the partial pressure of the gaseous components already inside the mixture is not going to change. That means the Kp value will not change. That means there is no change in equilibrium. As simple as that. Okay, right. Now we'll see what happens when I go for the next condition. That is when I add the helium gas at constant pressure. We will see what happens. Okay, right. So I think let me add a no. Let me just add it here only. It's better because I can just show it. Right. Okay. So now let me assume the balloon conditions. Right. Say now inside the balloon, I have a balloon, right? So inside this balloon, I have N2, H2, and NH3. All these things are there. Okay. Now this is a balloon. Assume that understand that it can expand, right? Fine. So now when I add helium to this, now what the condition says is that the total pressure PT1 should be equal to PT2. That means what? Even after adding helium, the total pressure should not change. That's what you mean by constant pressure conditions. Okay, last time the volume was was not able to change. In this case, the pressure should not change. Okay, now, so if at all I want the pressure to remain same even after adding equilibrium, what do you think will, how is it gonna happen? Tell me.
Could you repeat the question?
I mean, in the sense that even after adding helium, right, the total pressure is not changing. How can you do that?
We increase the size of the vessel.
Exactly, right? That's exactly what is going to happen, right? So obviously, what you see is that because of this, the pressure is expected to increase, right? But if this becomes bigger because of this, N2, H2, NH3, and helium are there, right? Now the balloon became bigger, right? So to compensate the increase in pressure, the volume has increased. Yes, right? So that means what? Here the pressure is going to remain same. In both these cases, the pressure is same, right? But in this case, but what has increased is the volume has increased. Volume of the vessel has been increased. Okay, now tell me what is going to happen. We already know what will happen if I increase the volume, isn't it? If I increase the volume, the reaction is going to move to a side where I have more stoichiometric coefficients. That's now we saw, right? So depending on the reaction, now in this case I can say that it is going to move backward direction, because you can see the reaction, it is going to be N2, right? N2 plus 3H2 giving 2NH3, right? Now this side where I have this side it's 2, this side it's 4. So obviously it is going to move in the backward direction, right? If I increase the volume. Okay, so again I repeat here. So now in this case, we're talking about constant pressure conditions, like in an addition of inert gas. So when I add the inert gas, now the pressure should not change. So what has to happen is this has to become bigger, right? So what you understand is there is change in volume after after reaching equilibrium, there is a change in volume, right? So we know what will happen if there's the change in, I mean, increase in volume. Increase in volume will always shift the equilibrium towards the side where I have more stoichiometric coefficient. So for this particular case, it is going to move towards the backward reaction. It is going to move towards the backward side, I would say, right? Okay, so understood. Constant pressure conditions, constant volume conditions. What will happen if I add an inert gas to the existing equilibrium mixture? Okay, so constant volume, there is no effect. At constant pressure, there is going to be increase in volume, so that the reaction is going to move to a side where I have more stoichiometric coefficients. That's it. So again, when I have delta n is equal to 0 kind of reactions, there'll be no effect. I told you delta n equal to 0 kind of reactions, all the volume terms gets cancelled. So even though there is an increase in volume, there is no net change in the equilibrium, right? Okay, now moving on to the last factor, which is going to affect your equilibrium, right? So the last factor which affects equilibrium is, I think it is the 7th one, I'm not sure. Yeah, right. Right, this is your catalyst. Okay, right. So we know what is a catalyst. Catalyst is going to increase or decrease the speed of the reaction. Okay, so you'll study more about catalyst, how they are able to do it, how they're able to help increase the rate of the reaction, all that in 12th class, right? I have a separate chapter called surface chemistry, right? So that is one there you will study even chemical kinetics. I told you there's a chapter called as chemical kinetics. There again you will study how catalysts are helping in increasing the rate of the reaction, right? So for now, what you have to understand is, people, catalyst in equilibrium, after I have reached equilibrium, or say I have a reaction like A giving B, right? Say now this is without catalyst. Now say same A giving B, I do in the presence of a catalyst. Okay, now what is going to be the difference here, right? So now please understand, people, the say this has Kc as the equilibrium constant. Okay, say this particular reaction, the first reaction has Kc as the equilibrium constant. Oh God. Okay, right, this is Kc, and this reaction, if you check, this is also going to have the same value of Kc, right? Whatever the equilibrium constant value I had for the reaction without catalyst, this is also going to be the same value. But what will you see that is changing is the time taken for the reaction to reach equilibrium. Okay, say assume that this takes say 1 hour. Right, say this takes 1 hour to reach equilibrium, right? Say this will take only 5 minutes, right? That is the difference, right? But the total equilibrium is not going to change, right? Because of this because of putting the catalyst, it is not like the reaction is going to move in the backward direction and the forward direction. But what will happen is the only thing which will change is the time required for the reaction to reach equilibrium will get decreased because of introduction of catalyst. Okay,
I
so
have a doubt.
yeah.
So we'll not include a catalyst, right, in Kp, Kc?
No, we'll not, because it is not going to take part in the reaction. Again, Kp or Kc will be B by A. That's it. Only the reactants
Okay,
and products.
understood.
Right? Okay, so that's it, guys. That's the first part of the chapter. Right? Equilibrium is actually one of the biggest chapters in your 11th syllabus. Right? So we have completed the first part. We started with what is equilibrium, what is equilibrium constant, law of mass action, QC, what are the properties of equilibrium constant, how do you do a problem, right? Then we went on to see what are the factors which is going to affect the equilibrium and all those things. Le-Chatelier's principle, thermodynamics of equilibrium. I gave you an equation connecting delta G naught and Kc, right? So all these things are there in the first part. Okay, right? So guys, it is mandatory for you to solve your, not only for this chapter, for any chapter, if you want to practice and if you want to have good quality problems, the easy availability is your NCERT book back. Please solve them, right? That is more than sufficient for you to understand the concepts and even for the problem solving. Okay, right? So that's about the first part. What is the time? We have 15 more minutes. I'll just give you introduction to the next part, right? So next part is still more problems, numericals will be there. Okay, so we are going to see ionic equilibrium. Okay, right. So till now we have been seeing only the reactants and products in the form of compounds, molecules, right? Now we are going to venture into ionic reactions, right? So ionic reactions in the sense we are going to see, you had a chapter in your 10th class, right? Acid, bases, and salts. Correct, right? So this ionic equilibrium is going to be a continuation of that particular chapter. I mean, this is going to be little like really higher levels of chemistry, right? For your compared to what you studied in your 10th class, that is acid, bases, and salts. This chapter is going to give you a lot of insight about acid, bases, and salts. Okay, right? So we know what we're going to do. We are going to predominantly only the last part we'll be dealing with salts, but most of the part, like say almost like 70% of the part, we'll be dealing with acids and bases in the acids and bases only. Okay, right. Now people, right? So we know first, okay, we'll just try to understand what do you mean by an acid or what do you mean by a base, right? So we already know the definitions, right? But I don't know whether you know all the definitions possible. Okay, so let me give you one by one, right? So when I say there are three theories, okay, there are three theories by which you'll be able to define what is an acid or what is a base, right? So the first theory is what is called as your Arrhenius theory. Sorry, right? It's called Arrhenius concept. Okay, this is your famous concept which you already know, right? So if you dissolve a substance, there's a substance, right? And if it is dissolved in water, right? And if this produces H plus ions, right? Now it is termed as an acid. This we already know, a very famous definition which you have been studying from your lower classes, right? So where there's a substance, if I dissolve that substance in H2O and if it produces H plus, actually it's not going to be H plus, it is H3O plus, hydronium ion. Anyways, we'll come back to this later, right? So whether if it produces H plus ions or H3O plus ions, it is going to be called as an acid. And same substance, or not same substance, different substance when dissolved in water, if it gives me a hydroxide ion, OH minus, it is said to be a base. Very simple, right? So please understand, you can, there is, okay, please, this thing, when I say HCl gas, right, is it an acid? Answer my question. I'm asking, HCl gas is there. Can I regard this as an acid? Yes, no? Hello?
We can, right, sir?
Okay, so please understand this. We define acids on and only in aqueous phase. Please remember that, right? So HCl, the moment you see HCl, you should not decide that it is going to be a gas. Sorry, I mean, you should not decide it is going to be an acid, right? So when I dissolve this HCl gas in water, then it becomes an acid. That's what you need to understand, right? So if I ask you, is a HCl gas an acid? The answer is no, absolutely not, right? If you dissolve this HCl gas in water, that's why I specified this. Only when you dissolve a particular substance in a solvent or particularly water, if you get these ions, then only I can call it as an acid or a base. Okay, not in their gaseous forms, not in their liquid forms, only in aqueous phase, AQ, only in their aqueous phase. I can define acids. Okay, fine. So this is what is called as Arrhenius theory, which we already know, right? H plus ions, whichever gives, is called acid. OH minus, whichever gives, is called a base. Again, when you dissolve them in water, right? Okay. Now we know that not you must studied even in your what is that chemical bonding chapter, right? So it is not like everything which doesn't give me H plus is not an acid, right? So there are substances which doesn't give me H plus or which doesn't give me OH minus, but still are regarded as acids or bases. Again, why? Because the pH value is in that way, right? So we'll talk so much about pH calculations here. Not only pH, we will calculate pH for so many substances. I'll give you a formula and we'll find out all that. So for now, please understand that there are substances which are not going to give me H plus or OH minus, but still are regarded as acids or bases. Okay, so Arrhenius concepts is not enough to define what exactly are acids or bases. Okay, so for that we have to go to the second one, right? So second one, that is second theory, which is going to help us define what are acids or bases. One second, guys. Right? So define what acids and bases. We already know, I think it's called Lewis theory, right? So in Lewis, we know, we already know studied about Lewis acids and Lewis bases, right? So what did I tell you there? I told you that whichever is able to, okay, fine. Actually, before this, guys, before seeing Lewis theory, we'll actually see this theory. Second one, we'll see is Lowry, Bronsted, right? It's Lowry, Bronsted theory, right? Okay, so what this theory says, right? It says, actually, guys, this is R. Why this touch is a problem? I really don't understand. Okay, this is R and this is O. Okay, right, Lowry, Bronsted, right? So what it says is that whichever is able to donate H plus, right, are called as acids. Sorry. What am I talking? Right. So whichever is able to donate protons are what are called as acids. Right. And whichever is able to accept protons are what are called as bases. Lowry Bronsted acids and Lowry Bronsted bases. How do you define them? Whichever is able to donate a proton. Right. See, what is a proton? Basically, H plus is a proton, is it not? Right. Hydrogen had one electron, one proton. Right. Now, when I say H plus, the electron has been removed. So what is remaining? Only one proton is remaining. Right. So this way is like it's not much different from much different from your result Arrhenius theory. But this one, right? Whenever I'm saying that I'm going to accept protons, it is going to act as bases. That definition was not given by Arrhenius, right? So how will I prove it? It's pretty simple, guys. Say when I have ammonia, for example. So when I have ammonia, now when I add H plus to this, you will be able to get NH4 plus, right? So what is happening? This is the proton. This is accepting the proton. So I can call your NH3 as a Lowry Bronsted base. Okay, whichever is able to accept a proton is going to whichever is able to accept a proton is going to be called as a base. That's my Lowry Bronsted theory. Okay, donating protons, acids, accepting proton bases. Easy, right? So now we'll move on to the third concept and I'll finish with that, right? So that, which we are, again, we already studied this in your chemical bonding chapter, and that is my Lewis theory, right? So Lewis, now your Lowry-Brownsted theory spoke in terms of protons, right? So your Lewis theory is going to speak in terms of electrons, right? So we already know what happens here, but still I'll tell you again. So here, whichever is able to accept electrons are what are called as acids, right? And whichever is able to donate electrons are what are called as Lewis bases, right? So we already saw some examples. We'll just see it again. Say, for example, if I have BH3, right, or BF3 or whatever it is. Now you can see B, or again, let me take BF3. That will make sense, right? Say BF3. Now if I add an electron in the form of F minus, okay, F minus is fluoride ion. Now what will you form is BF4 minus, right? So we know why is it able to do this, because I'm going to have an empty orbital, if you can remember, right? And here I'm going to have a coordinate bond formed, right? So this F minus electron is going to attack BF3, and that is accepting the electron. So BF3 is going to be called a Lewis acid. Okay, right? And whichever is able to donate an electron, say NH3 has a lone pair, right? Now, if I say I have an H plus, right? Now this lone pair is donated to this H plus, forming a coordinate bond, right? So I can call ammonia as a Lewis base. Okay, so whichever is able to donate a lone pair is called a base, Lewis base. Whichever is able to accept a lone pair is what is called as a Lewis acid. So these two are the example. This is a Lewis acid, this is a Lewis base. Okay, so these three things you have to know. What is Arrhenius theory? Arrhenius theory is in terms of H plus and OH minus. Next, your Lowry-Bronsted theory is in the form of protons, which are able to donate protons is called acid. Whichever is able to accept proton is called a base. So we saw here, if you can look at the examples, right? So NH3 is accepting proton to form NH4 plus, right? Now here, the last theory is Lewis theory. It talks in terms of electrons, which says that accepting, whichever is able to accept a lone pair of electron like BF3 is going to be called as a Lewis acid, and whichever is able to donate a lone pair of electron is what is called as a Lewis base. Okay, so we'll continue further, guys. We'll continue further in the next class. We will be speaking about the qualitative aspects and the quantitative aspects of acids and bases. Okay, so we'll continue. I think I'll be required after this. I'll have only 2 more chapters. So now this is December. So I hope to complete it by January end. That's what I'm planning. Okay.
So
So
I have a doubt.
yeah.
Like, what is the name of this? Lewis.
Lewis theory. That's it.
Lewis
Lewis theory. Yeah, Arrhenius theory, Lewis theory, Lowry-Bronsted theory. All these are theories. Okay, right? So I will be completing your chapter by max January end or say February starting. Like I'll just try to complete it, but GOC, that in general organic chemistry, is again so big. Okay, so fine. We'll see what can be done. Right. So I hope. Is there any questions, people?
So could you just show that Lowry-Bronsted theory?
Yeah, sure. Yeah, this is your Lowry-Bronsted.
So could you explain that example once again, sir?
Yeah, sure. So what happens here, right? So donating proton, any acid, say anything which can give me H plus. H plus is a proton, correct? So H plus is a proton. Anything which can give me H plus is going to be this thing, right? So anything which accepts H plus also is going to be a base. That's what he's telling, right? So you have ammonia here, right? So this ammonia is accepting H plus to form ammonium ion, NH4 plus. right? So this ammonia is a Lowry-Bronsted base because it is able to accept a proton. And anything which donates a proton, anything which donates H plus is going to be called as a Lowry-Bronsted acid. That's it.
Understood, sir. Thank
Right? Okay, guys, we'll meet on Monday, right? So fine then. Till then, thank you. Bye bye. We'll meet again.
you, sir.
Thank you,
Yeah.
sir.
Thank you.